area examples are area between curves. So the next sort of set of notes is going to be looking at specifically area between one function and another function. All right, the first case is if our two functions don't intersect, meaning one function is always bigger than another function. All right, they never cross, at least they don't cross over the region we're looking at. They may cross later or earlier, but they don't cross over the area we're looking for. All right, so we want to find the area bounded by two graphs. And what happens here is actually something very unique. Alright, so first the area between these two curves that do not intersect over the given interval. Again, they might intersect outside the interval, but between point A to point B, they never cross. Alright, never cross. Alright, so to find the area between two functions, given that they're both functions, and I know and for some reason it did this weird, but f of x is greater than g of x. For all x in the interval a to b. Alright, again, if they don't intersect, one function has to be bigger than the other function over the interval. Then the area between the functions is found by taking the bigger function minus the littler function over that area a to b. And so this finds my area between f of x and g of x over the interval a to b. And again, it's important that this is the bigger function. I'm going to take the bigger function minus the littler function. And so what's happening there graphically, alright, so suppose I've got f of x and then g of x. Alright, now this is my a and this is my b, so this is a to b. And so the area I'm looking at would be the area between these two functions. Right? This is the area I want to find. And so what's happening there is, well, remember what the area is. It's the accumulation of all the function values under f of x. So I'd be adding up all of these values. That would be the area under f of x. And then I would be taking the area under g of x. And it's easier, the reason why I drew it negative, because it's easier to understand that why the subtraction works. Right? This area would be negative. Right? If I add up all of the g values, they're negative. And so when I take f of x minus the g of x, would be minus the negative area, so it would become a plus. We add to it. And what actually happens is something very unique. When we take, let's suppose I get my new function y equals f of x minus g of x. Right? So this would be a new function, where I take my function f of x and subtract my function g of x. And so what happens is my y values get added together, right? I take this y value and it will add this y value. Even though it's a negative, I have a y value there, I take y value from my function 1, subtract the negative y value from my function 2, and so it would actually be the y value from my function 1, and I'd add it to my function 2. And so what we get is a new function. Alright, so this would be the new function y equals g of x minus f of x minus g of x. If I go from A to B, this area, which I can solve with the fundamental theorem of calculus, right? I can find this by integrating. This area, now it's a different shape, but it's exactly the same as this original area here. And I'm going to do that in an example. I'm going to graph the area between the functions and then graph the area when I combine the functions. And what happens is, even though the area's shape is different, the area size is the same. And so this area here is the exact same size as this area here. And that's actually unique. That's kind of an important thing that happens. And we're just going to practice solving it. But that's what's happening here in this theorem. Alright, so that's what's happening here in this case, the area between the two functions. Alright, so I'm going to do my first example. And I'm going to show you the graph of the regions. Alright, so suppose I have these two functions. I want to find the area bounded by the curves f of x and h of x from negative 2 to 2. Both of them are this first function h of x is a line, continuous everywhere. F of x is a parabola, right? X squared is a parabola, continuous everywhere. So first I'm going to show you that f of x is greater than or equal to h of x from negative 2 to 2. Actually, I believe it's always bigger than it. And I'm going to do this by just showing you it graphically. Alright, so I'm going to graph the two functions. Alright, and I'm going to give the area once shaded in and integral we need to solve. So I think I already have them in my graph here. Alright, so there's f of x, which is x squared plus 4. There is my h of x, which is the negative x minus 3. And so a standard window is what I use. So I hit standard and graph. Alright, so the blue function is f of x. The red function is h of x. And so you'll see, actually, in this case, f of x is always bigger than h of x. And we're just looking between negative 2 and positive 2. Alright, so again, that holds true. So I'm going to go sketch the picture in my notes. Alright, so the area we're looking to solve is my parabola f of x. So there's f of x. My line, g of x. Or not g of x, h of x. H of x. From negative 2, right, negative 2 to positive 2. Right, so this is the area we want to solve for. Right, I want to find this area. Well, I know f of x is greater than h of x over that interval negative 2 to 2. And so that previous theorem I stated means I can find this area by integrating between negative 2 and 2, the bigger function minus the smaller function. And so the bigger function was f of x. And so f of x was x squared plus 4. Subtract the smaller function, which was the negative x minus 3. If I solve this integration, I find that area. And so I'm actually going to simplify this integral, negative 2 to 2. Make sure you're careful here. Distribute that negative, so it's x squared plus 4 minus a minus gives me a plus x and a plus 3. And so the area I'm looking for is actually solving the integral from negative 2 to 2 of the function, the new function where I've subtracted. Which gives me the function x squared plus x plus 7. Alright, so I'm going to go graph this. I'm going to go to my graphing calculator, and I graph that area. So I'm going to go here. I'm going to clear out the ones I have. Clear. Actually, I'm going to use that because it's close to what I want. Plus 7x plus 7. Oops. Delete. Alright, so make sure I type that in correctly. X squared plus x plus 7. Alright, graph. Alright, so now it's a parabola that's open in there. And so there's this new function. Actually, it's nice that they drew it in a different color. It's negative 2, so it's a parabola that's opening up here, and it is, right? X squared gives me a parabola that's opening up from negative 2 to 2. So if I go graph this on my paper, I don't know why sometimes it does that. Alright, so negative 2 to 2, it's a parabola that's up here. Alright, that's the new graph, f of x minus h of x, which comes out to be that y equals x squared plus x plus 7. I find this area. Now it's a different shape, but that area is the exact same size as this area here. Right? They're a different shape, but they give me the exact same size, which then I can find that on my calculator using the fundamental. I popped up the wrong thing. All right, so I'm going to shade it in. I'm going to hit second trace, negative. I'll clear. Second trace. Pick my 7, then type in my negative 2 and my positive 2, and it'll shade that region in, and so that region comes out 33 and a third, and so there's my answer. That area is 33 and a third, which is exactly the same as this area, which we actually found was 33 and a third, and so the answer is the area between f of x and h of x over negative 2 to 2 is 33.33 repeating 33 and a third. with what that area is. All right. And so again, it's kind of unique. It's kind of a nice thing that happens. All right. And we'll practice this in more examples in the next videos.